Alright, this is our last lesson in this chapter. This is continuity. We have talked about discontinuity in the past. It was last semester where we talked about vertical asymptotes and holes. If you remember, vertical asymptotes happen when the denominator equals 0, as long as the bottom doesn't cancel, and you have a hole. If you ever can cancel a factor on top and bottom, then whatever makes that factor 0 is your hole. And then there's a jump, which I don't think we talked about last semester, but these occur most often in piecewise functions, and you use one-sided limits to be sure or to determine whether or not there is a jump. There is also a limit definition of continuity, where the idea behind finding whether or not a function is continuous is this thing right here. If the limit as x approaches some number of a function is equal to f of the number, that's what we have to prove to show that something is continuous. Now that doesn't make a whole lot of sense because it's weird unknown functions and stuff. I'm going to put in a number. So let's just say, for example, instead of x approaching a, let's say I knew that the limit as x approached 3 of some function, I don't know what the function is, but let's just say the limit as x approached 3 was 4. Well, what that means graphically is that as my function approaches the x coordinate of 3, so I'd go over 1, 2, 3, as I get close to 3, this limit, which is both sides, the function is coming in towards a y coordinate of 4. So on the left side of 3, I'm coming in at 4, and on the right side of 3, I'm coming in at 4. All I know is that left and right sides both go towards 4. I don't know what's happening way far away. Also, a limit can exist if there is a hole there. So what I have right here is I've drawn some function so that the limit as you approach 3 is 4. Left and right sides are both going to the same place. So the limit does exist, but I still have a hole. This is not continuous yet. So to make this a continuous function, you have to fill in that hole. And the way I fill in that hole is I make sure that it's known that f of 3 is equal to 4 also. F of 3 means that's what's happening when x equals 3. So if f of 3 is equal to 4, then that fills in the hole, and now my function is continuous. So that's what this thing is saying right here. If the limit as you approach a number is the same thing as f of the number, then you have a continuous function. Let's find some discontinuities here. We're actually going to put that limit thing on the back burner for now. If I want you to find discontinuities, first thing you want to do is make sure everything is factored and canceled. Now number 1 here is already factored. There's nothing you can factor here. So if I want to find a discontinuity, I look at my denominator and I set my denominator equal to 0. X plus 8 equals 0. And then you subtract 8 from both sides of the equation, and you get negative 8. Now, x plus 8 did not cancel. That's something that is still in the denominator. You didn't cancel it with an x plus 8 on top. Since that did not cancel, this is a vertical asymptote. Or you could call it an infinite discontinuity. I will accept either one of those. An infinite discontinuity. So there is your answer for number 1. Okay, number 2, this one is not factored, so let's factor number 2. X squared minus 9 is a difference of squares. That's x plus 3, x minus 3. On bottom, factors to x plus 1, x plus 3. And I notice that x plus 3 cancels. If something cancels, that factor creates a hole. Whatever canceled makes a hole in the graph. So I will have a hole, or a removable discontinuity, wherever x plus 3 is equal to 0. So I will subtract 3 from both sides, and x equals negative 3 is a hole, or you can call it a removable discontinuity. Removable. I think I misspelled removable. Oh well. Okay, then I also still have an x plus 1 in the bottom. This did not cancel. If a factor doesn't cancel, then that creates a vertical asymptote. So I have a vertical asymptote wherever x plus 1 is equal to 0, and I will subtract 1 from both sides, and you have a vertical asymptote or an infinite discontinuity. discontinuity at x equals -1. So you factor and cancel. If something cancels, that's a whole. If it does not cancel and you still have it in the bottom, then that is a vertical asymptote. Now the last kind, this is the most confusing kind, is the possibility of a jump. And that's when you have a piecewise function. This is piecewise because we have two different pieces, two different functions that make up the whole equation. And our possible jump occurs wherever you make the transition from one equation to the other. And in this problem, that's number 3. So I have a possible jump at x is equal to 3. And the way you test to see if there is a jump is you look at the left and right hand limits. So I'm going to look at the left side. And I want to know, okay, what is the limit as x approaches 3 from the left of this function? Well, the left side of 3 is when x is less than 3. So here's my left side up here. And the left side is given by the equation 2x plus 1. And if I plug 3 into that, 2 times 3 plus 1 is 7. So I know that the left side is approaching 7. Then I want to look at the right side. So I'll look at the right side. And my right side is when x is greater than 3. So I'll do the limit as x approaches 3 from the right of my function. Okay, and the right side of 3 is given by the equation x squared minus 1. And when I plug 3 into that, let's see, I have 3 squared minus 1. 9 minus 1 is 8. Okay, so I'm looking at this. My left side and my right side are going to two different places. If you get different answers, that means there is a jump. So there is a jump at x equals 3. Left and right sides were different, therefore there is a jump. And if you want to look at this graphically, what's happening with this one is the thing that I'm worried about is happening at 3. So when I'm at 3, here's 3. I have two things happening. One function's coming in at 7. I'll put 7 right here. And the other one's coming in at 8. This is not drawn to scale. And the left side is going towards 7. So when I'm on the left side of 3, my function comes in at 7. My function's right around in here somewhere. However, the right side of 3 is coming in up here at 8. They are not going to the same place. That's why we call this a jump. So I go from the left side coming in at 7, then I jump up here at 8, and that's where we continue the graph. Let's see, determine whether these functions are continuous. Now we're going to look at that limit definition. A function is only continuous if the limit as x approaches 2 of your function, or I'm going to say a, x approaches a of your function is equal to f of a. So what I've got to do here is I need to find the limit as x approaches 2 of f of x, and I need to find f of 2 because that's the point I'm worried about. So f of 2 is always the easier one. Limits take a little bit more work. F of 2, this means we want to look at when x is exactly equal to 2, and that happens on this top equation. This is x less than or equal to 2. So I would say f of 2 is 3 times 2 minus 1, which is 5. So I know that f of 2 is equal to 5, and we'll kind of put that on hold for a minute. So I know what f of 2 is. Now I need to find the limit as x approaches 2. And when you're doing limits, if you have a piecewise function, I have to look at both sides. So I have to look at both sides. I'm going to start by looking at the left side. Okay, what is the limit as x approaches 2 from the left of this function? Okay, well, the left side, that's my top equation. X is less than 2, so that's the left side of 2, so that'll be the function 3x minus 1. And when you plug in 2 for that, 3 times 2 is 6, minus 1 is 5. So my left side's approaching 5. Now I need to look at the right side, which would be the limit as x approaches 2 from the right of this function. And the right side of the function is when x is greater than 2, so I'm going to plug it into x cubed minus 3. 2 cubed is 8, 8 minus 3 is 5. And then I look at this and I notice that my left and right sides are equal. If left and right sides both go to the same place, that means, therefore, the limit as x approaches 2 of your function is also equal to 5. And so now I look at this limit. The limit is approaching 5. F of 2 was equal to 5. And since f of 2 is equal to the limit as x approaches 2, that means I can use these two things right here to say that f of x is continuous at x equals 2. And the reason is because the limit as x approaches 2 of your function ended up being the exact same thing as f of the function. So there is the answer with justification. So there's number 4. Let's try this one. Is this the last one? Yeah. Number 5, last one. Determine whether we are continuous, and I should have said, I meant to say at an x coordinate of 1. So we want to know whether this function is continuous at x equals 1. And we're going to do the exact same thing. We're going to do the limit as x approaches 1. We need to find that answer. And then we need to find f of 1. And we need to see if those two things are the same. I think the f of 1 question is always easiest because that's when x is equal to 1. And when x is equal to 1, this function is at 9. So f of 1 is 9. So I'm going to put that on hold for a second. And I'm going to see if my limit ends up being the same thing. But again, we're going to have to look at left and right sides separately because this is a two-sided limit. Limit as x approaches 1. I'm going to have to look at the left side first. I guess you could look at the right side first. I'm doing left side. So limit as x approaches 1 from the left of your function. And the left side of 1, that's when x is smaller than 1. So I'll plug into the function 5x plus 1. And if I plug in 1, 5 times 1 is 5. Plus 1 is 6. Okay, so there's my left side. Then I'll do my right side. And limit as x approaches 1 from the right of your function. That's going to be this bottom piece down here. And the right side is the function 6x, and 6 times 1 is 6. And then I'll look at my two answers. My left side and my right side are both going to the same place. Therefore, the limit as x approaches 1 of my whole function, so I'm looking at 1 from both sides, that limit is 6. Well, then I look up here and I see that the limit is approaching 6, however f of 1 is 9. These are not the same. So from this point I would say, alright, the limit as x approaches 1 of f of x is not the same, is not equal to f of 1. It was 6 and 9. They are not equal to each other. Therefore, the function is discontinuous. Therefore, f of x is discontinuous. And the type of discontinuity, I want to do this, show you this real quick, and then that'll be it. The type of discontinuity, we have vertical asymptotes, we have jumps, and holes. So the way we figure out what type of discontinuity this is, I'm going to kind of sketch this graph really quick. And what I know is that first, f of 1 is 9. This is an ordered pair, 1, 9. This is like algebra 1 stuff. So I'm going to start by plotting the point. When x is 1, my y coordinate is 9. So I have a point up here. However, the limit as x approached 1 was 6. My limit does exist, and if the limit does exist, that means left and right sides both go to 6. So as I get close to 1 from the left side, my left side is coming in at 6. My right side is also coming in at 6. And what I'm going to have right here is a hole at x equals 1. Because at x equals 1, my point for the graph is way up here. So what we've got is a hole / removable discontinuity. And there you go. So there's a little bit of stuff on discontinuities. Hopefully that makes some sense.